Okay. So last time, if you remember, we were looking at first derivatives. So what we're going to have a look at today is using first derivatives to help us find something called turning points. Okay, so we should start off by saying exactly what a turning point is. Guys, are you ready? Yeah. A turning point is a point in which the derivative, the slope of the tangent, is 0. That's all it is. So if you were to look at it as a picture, so you see here the tangent is positive, here the tangent is negative, but right on the top here the line is horizontal. This is where we have the turning point because the slope here is 0. Now we've seen something like this before in quadratics. What is this also called? Vertex, yeah. So it's also called also known as a vertex. But when you look at the picture, you realize, oh, you could also call it a maximum. But of course, I could have drawn my graph upside down, so it could have also been easily a minimum point as well. It's also called a stationary point, etc., etc., etc. So there's many different names for this, but it's all the same idea, that the slope of the tangent is 0. Okay, so let's do a couple of examples where we find these turning points. Let's start with a quadratic, because quadratics, we learned one method already, completing the square. So let's have a look at a quadratic. Scroll down. Yeah. No. Okay. So what I'm going to do is I'm going to find the vertex for a quadratic using both methods. We can see how the derivative is actually a quicker way to do it. Okay. Got that? Yeah? Right, so let's take this quadratic. Y equals x squared plus 2x plus 5. Okay? Completing the square gives you x plus 1 squared plus 4. So where's the vertex? -1. Vertex is at -1 and 4, yeah. Okay, so we could have used the formula we saw earlier, where you calculate the derivative, make the derivative equal to 0, and then this gives us exactly the same value for x. If you sub that in, you'll get y equals 4. So you get the same answer. However, the advantage of using this method is that it works for any problem, whereas the completing square only works for quadratics. Okay, so we'll have a look now at a cubic. Yeah?
You got -1 for x.
Yeah.
It makes the x 0?
Yeah, makes the derivative 0. Yeah. Okay. Can I scroll down? Moza? Yeah? You sure? Yeah? Okay. So, before we start the cubic, if you think about its shape, be something like this. How many turning points are there on this? 2, yeah. You've got one here and one here. Okay, so let's find it. Let's take this one as an example. Y equals 2x cubed plus 24x squared plus 96x plus 30. Okay, so the derivative is going to be 6x squared plus 48x plus 96 equals 0. I think I can divide by 6, so that will be x squared, is that 8? And that is 1/6. This has two solutions. Or this one actually has one solution, doesn't it? So you get x equals -4. Now the reason that there's one solution, it must be that the cubic looks like this. And yeah, if you look here, well, I'll draw it a bit more accurately. Before I draw it in, I want you to look at this and just visualize. Can you see where the turning point is on this graph? Where would the tangent line have 0 slope? So, yeah, well, I suppose kind of around about here, yeah. Because if I draw a tangent line here, see, this is where the graph is leveled off. So there's only one for this particular cubic. Okay. Let's do another example now, but I'll let you just try one before we do some more. So I'll just give you a quadratic just to get you started. Oh, and by the way, you always need to get the y here as well, but I'll have to open my calculator to do it. So I just want you to try this one. Give me the turning point, the vertex for this one. Let me open my calculator. Yeah.
-16?
Yeah. Yeah, sorry, -16x. I don't see a lot of views on my trigonometry videos. Remember, I recommended that you look at those videos because all the solutions are there in one of the videos. If you're in group 1, you need to watch part 2 or the other video, and vice versa. Okay. Right, we should be getting answers now for this. So the derivative is 2x minus 16 equals 0. So x equals 8. And if you put that in there, did anyone get the y yet? -72? Yeah? Yeah? Let's graph this to check. So if I type in y equals x squared minus 16x minus 8, let's graph it. Let's zoom out. So would you say that the derivative is at 8 and minus 72 here in the picture? That looks right to me, doesn't it? Yeah, okay. Right, I'll give you a cubic and then I'll do a different one now. So let me give you a cubic. So let's try what was the cubic I gave you a moment ago?
2x cubed
Yeah.
plus 24x.
Okay, so you can try this one for me. 2x cubed plus 18x squared plus 54x minus 24. that answers that. So the derivative here,
6x
yeah, 6x squared plus 36x plus 54. Again, can we divide by 6? Yeah. Yeah, so 3 and 3 again. Okay, I wanted to give you one that had two different ones, doesn't matter. X plus 3, x plus 3. So you get x equals minus 3 and then y equals minus 17? 78 then. Okay. They don't always work out like this. They do have two solutions, okay? Question?
Yeah, do we substitute x into the
Original.
original, not
Yeah.
the derivative?
No, because you know that you will get 0 if you sub it into the derivative, because the point is you're finding the x to make it 0. Okay, I want to have a look at another another cubic here. Let me just delete this stuff here. Right, let's do this one together. So I want the... Oh, let me just make it y e... No, I'll just leave it like that. Okay, so we want to find the turning point here. So what's the derivative of this one? It'll be 3x squared plus 3. Okay, so let's get the derivative here. So you get 3x squared plus 3. And if we want the turning point, what do we make this equal to? 0, so there it is there. Okay. Now we can simplify this a bit more, can't we? Because there's a 3 and everything. So I'll just take it and divide by 3. Oops, simplify. Okay, so right, so had my cubic, got the derivative, there it is there, made it equal to 0, and divided by 3, and I got this. But what's the x here? What's the solution? Mm-mm. Yeah, that's it. There's no solution here. So this means this cubic has no turning point. This one has no solution. Say again? Well, that's interesting, isn't it? Because you would imagine, how can we draw a cubic that doesn't have a turning point? So let's actually graph this and see what we get.
Sorry, Stephen.
Yeah.
Instead of saying no solution, can you say I?
No real solution. So this is how it looks. Let me zoom in to help you out here. So the only place it could maybe possibly have a turning point is in the middle. But you notice that it never quite levels out. You know, there's no part in this graph that's flat. It's always increasing. It never levels out. If I zoom out now, like it looks like it might be here, but when you zoom in, you realize, oh no, it's not in the center because it has a positive slope here. Okay, so there's no guarantee that cubics will have turning points. You are guaranteed though that quadratics will have turning points. I mean, I could never make a quadratic not have a turning point, because when you picture the quadratic, it goes either like this or like this. So it has to have a turning point. Okay, but cubics don't have to have a turning point. Okay. Let's do another one now. We'll make it a little bit harder. So let us do this one here. Y equals log x 18 plus x squared plus 12x minus 8. Okay, what do I need to do first here before I could even start to differentiate?
Get rid of the log.
Yeah, well, not get rid of the log, but do something with the log. Can I differentiate this? Can I? No, I can't. Not yet. The 18's the problem.
18 is not...
Bring the 18 down. Yeah.
18 over x.
18 log x plus x squared plus 12x minus 8. Yeah, so the derivative then is 18 over x plus 2x plus 12, and we want that to be 0. I can divide by 2, And what should I do next?
Multiply by x.
So I get 9 plus x squared plus 6x equals 0.
3.
Yeah, what's we've got x squared plus 6x plus 9 equals 0. 3 and 3, is it?
Sorry,
Yeah.
Derivative
Yeah.
of lineage.
Were you in yesterday? So catch up. You can watch the video. Yeah, like and subscribe. Did you watch the video yesterday for the lesson that you missed? Did you? No, so I'm not going to catch you up now, so you'll need to get that yourself, okay? I gave everybody a table yesterday. Right, x equals minus 3. Okay. If I sub that back in, I'll get the y. So let's sub that back in. So that's log. Now you have to be careful, you might need a double bracket here. Minus 3 squared plus 12 times minus 3 minus 8. So minus 15.22 is what I got. Let's have a look at this graph now in a moment. So, this graph has only one vertex. So what shape might we think it's like? What graphs have one vertex? Quadratics, yeah? Or sometimes cubic. Okay? So we'll have to see what shape we get here. But we expect a vertex at this point. Okay? Do we think this... Now, we haven't really talked about it. My graphs are gone here. Do we think this vertex might be at the top or at the bottom? Could it be a maximum or a minimum? Yeah, and what's the reason we think for this? The negative, yeah? So, okay, so prepare to be surprised then. Okay, so let's have a look.
No, I feel like it's going to be a maximum because of the negative.
Because of the negative?
Oh, no, I just feel like it's going to be a maximum.
No, but
I think it should be minimum because of the equation.
The way the equation is structured, yeah. Let's have a look. Y equals log, what was it? X power 18 plus, what was next? X squared. Minus 8? Yeah. Okay. I don't really need the y. Okay, so let us graph that.
it's a weird shape.
Yep, it is. Let me just reset. And I'll zoom out. Yeah. Now, where was our turning point? Minus 3 and minus 15. So that's actually here. Minus 3, minus 15. And we can see, oh yeah, okay, it does level off here. Let's zoom out a little bit more perhaps. Trying to get the scale. But yeah, okay, that's a little bit clearer. Here, the tangent line. You can imagine if I drew a tangent here, it's horizontal. Yeah. So that's actually maximum because its neighbours are less. Yeah. But it's not a global maximum. It's not an overall maximum because there's part of the graph here that's higher than it. You know. But you might notice something strange here. We said there's only one turning point, but if we look at this graph, it looks like there's two, doesn't there? There's like one here and possibly one here. So let's just zoom in on this point. Where's center on cross? Center on cross. Okay, and zoom in. So it looks like so about 0, minus 90. Okay, so let's zoom in. Okay, no, maybe it's about minus 100. Okay. Center on cross. Oh, now it's maybe 115. All right, well, let's center on cross again. And zoom in. And that's 126. So somebody might realize what's actually happening here. what happens as I try to figure out what that turning point is? Yeah, because what's happening? Yeah, it's just going straight down. It's actually shooting down to infinity. It just looks like it stops at minus 80, but when you actually zoom in, you see it still continues to go down. And anyways, I can't really look at x equals 0. Why should I not even be considering it? Yeah. If you look back at this equation at the beginning, what values of x can I not use? No. And anything else? I can't actually use minus 1. The only value I can't use is 0. Why am I allowed to use negatives here? The 18 power. 18 power makes this always positive. So, in fact, I'm only not allowed to look at 0. Which, makes sense because you do have a graph over here. And you do have a graph over here. Yeah? Okay, let's see.
So it's never actually connected, it's just two parts of the arc.
Yeah, they're not actually connected, you're right. It's like they're disconnected at the center. So it's almost like you have one graph here which levels out at minus 3, asymptotes, yeah. And then you have another graph which is like this. But there's no actual turning point on this half. Yeah. So, we realize in the next lesson we'll have to talk a bit more about what's called the nature of the turning point. Is it a maximum? Is it a minimum? What shape is the graph at the turning point? And then this is where the second derivative comes into play for those who've seen it before. Okay, so I just see if there's anything else there. Yeah, I'll just give you one short one to try, and then we can have a look at more in the book here. Wait, no, should I make it easy or hard? Oh no, I'll give you an easy one. No. We'll do it. Maybe we'll do an easy and then a hard one. So I want the turning point for y equals sine x, and I just want you to keep the x between 0 and pi. Oh yeah, that reminds me. I didn't say this last time. If I write sine 20, am I in degree mode or radian mode here? Radian. Yeah, not degree. Yeah, how did I know that? No.
There's no degree circle?
Yeah, there's no degree sign. Now you have to be careful in the exam, because sometimes in the exam, they might say something like find dy dx when x is equal to 2. And they mean 2 radians because there's no degree symbol. Now you have to be very careful with that. It's so common to have students use the wrong mode on the calculator. Okay, so my little tip here is to always use radians unless you see a degree symbol. Okay, so if you're asking me what mode should I use, the answer is always radians, unless you can show me a degree symbol. Okay, right, try this one. Give me the turning point here of this. Did you get the y as well? So if you look here at the graph, the derivative is cos x, which we need to equal 0. The cos inverse 0 is pi over 2. If you put that value back in, you get y is 1. But that's hardly a surprise, because we learned about the sine graph. So if we're just looking at the graph between 0 and pi, we are not shocked to learn that the turning point is in the middle at pi over 2 and 1. It's not really surprising. Yeah.
You go from cos x to pi over 2.
I did cos inverse 0.
Oh,
Yeah.
Radian mode.
Radian mode, yeah.
Is it possible to always solve by just knowing like you have to convert 180 to pi?
What do you mean?
For example, like I'm solving in degrees mode. Once
No,
I
no,
see, like,
solve in radian mode. It's simple. Always use radians unless you see a degree symbol. Yeah? Yes, yes.
What is 1.57? Sir, one more.
That is pi over 2. Huh?
One more example.
What type?
Really hard.
A really hard one. Okay. Okay.
Trigonometry 1?
Well, a harder trigonometry one, huh?
Yeah.
Can I scroll down? Can I scroll down? Right. Give me the turning points for this one. Y equals a half e 2x minus 2e x plus 1 plus e squared x plus 1. Let me make the graph for you before you start it so you can have at least a rough picture in your head of what's going on. So it's a half e to the power of 2x minus 2 e to the power of x plus 1 plus e to the power of 2 plus 1. Is that it? That looks like it. Right, okay. So looks like there's an answer somewhere around about the 1 3/4, 1.5 maybe, somewhere around here. That's what the graph looks like. So I'll let you try and find it now. Okay. Got answers anywhere? No? No? Mariam, it's only a fly. It can't possibly hurt you, don't worry. It's 500 milligram fly. It couldn't possibly hurt you. Right. Shall we look at the answer now?
Yeah.
Yep. So the derivative, well, actually before I do that, maybe I'll just clean this up a little bit. So I'll change this into half e2x minus 2ex plus e squared x plus 1. So this is a constant, this is constant, this is a constant, and this is a constant. So you learned that the derivative of e2x is 2 e2x. And what would be the derivative of ex? Ex. And this is tricky, or e squared x? E squared. It's like kx. And 1? 0. And this should equal 0. Okay, well, that cancels that. So you're left with e2x minus 2ex plus e squared equals 0. Comes with what? For this one? Oh, okay. Then it has no turning point, but let's see. I think it does, though. What type of equation is this? Let me write it a little bit clearer. Ex squared minus 2ex plus e squared equals 0. Quadratic, where the variable is ex. So, I'll try to factorize it. You have an ex and an ex. Now, listen carefully. You're looking for two numbers that multiply to make e squared and add to make 2e. Minus e and minus e. Is it? Okay. Minus e by minus e is plus e squared. Minus e add minus e minus 2e. So you get two answers that are the same. So you have ex equals e, which equals e power 1. So therefore, x equals 1. Yeah. Sorry. No, x equals 1. Ex equals E1. Therefore, x equals 1.
Sorry, I don't understand that.
The last line. Ex equals E, which equals E1. Ex equals E1. X equals 1. Yeah?
What happened in the first one?
Hang on, let me just number these. 1, 2, 3, 4, 5, 6, 7, 8. Okay, which line?
Third line.
Okay.
Yeah, the first one. Divide the x equals to 1 over 2, 2x, 2x. Where did the 2 come from?
The formula, remember, is enx. Its derivative is nenx. Okay. We haven't got the y yet, have we? So it was minus e plus 1, minus 2.69. Okay. Oh, the half is in it. Yeah. Okay. Yeah. All right. So that's the point. Let's see if that matches the graph. Okay. So 1 and minus 2.69. Okay. So let me just zoom in here. Yeah, okay, it looks like it could be at 1, and this looks bigger than minus 2.69. You sure you didn't make any kind of mistake putting in the 1? Let's check on the calculator. A half. Hang on. A half. E. Where's my E on this calculator? Shift E. 2 minus 2 shift E squared plus shift E squared plus 1. Okay, so... Oh, do you know what? I was looking more at this point, whereas I should be looking up a little bit higher because it's going straight across here. Yeah. I wonder actually, I think I can draw the tangent in on this program. Let me see, tangent of equation 1 when x is 1. Let's see. No. Tangent oh goodness. Alright, I don't know how. Oh wait, I know what I'll do. Alright, there we go. Can you look up? So I just drew in the tangent line at minus 2.69. So this is the line y equals minus 2.69. So you can see that it is indeed a tangent at the point 1 here. It matches up nicely. Let's zoom in a little bit. You see? Is that a bit clearer? Yeah. Yeah. Okay, so what I want you to try now, I want you to do one of each, a quadratic, a cubic, and a log. So I think it will be good to do. Can you circle these questions? 2, 3, 4. And 27. 2, 3, 4, and 27. Can you start those now? To the notes. Let me just close this. You can just pick some out randomly. It depends which types you find harder. I can just tell you in the exam they like to give cubic. So if you want to do more cubic ones, I recommend then that you do, let's see, number 8 as well. Number 8 as well. Question, yeah? Sorry, let me just write down something here. One sec. 2, what did I say? 2, 3, 4, 27, and 8. Yeah. Guys, there's these questions, 2, 3, 4, 27, and 8. Alright, what's your question there?
No, I just hear when I type and
It's this. You see, the calculator doesn't understand where the 18 goes. It's not sure if it means, is it on the minus 3 or is it on the log of minus 3? So the double brackets help. Yep. Can I close this? Hello? Can I close this? Yeah?